Let's discuss the tunnel effect and its application. And I'll start from some theoretical conditions, and I'll try to explain how all the realized formulas based on the quantum mechanical propositions can be used for the further uh, application of this uh, effect for some practical issues. And let's start. Okay. Let's consider some theoretical problem, fundamental problem in some case, but every fundamental problem should have, as a result, some practical application, and it will be discussed a bit further and some at the beginning. And let's see. For example, now I'll have one dimension, and in this form I introduce you some potential barrier that has its position from 0 to a at 1x dimension. And it's not enough clear what does it mean, this barrier from the practical point of view, but I'll try to represent it a bit much more useful. And let's introduce some model where we have particles with energy E that is lower than potential barrier U0. And let's see how could it be represented using some physical implementation. Here are some area. Of course, it's not absolutely correct, but from some points of view it can give us some understanding. We have some area of A dimension, and let's give you some atoms here. That's a crystal lattice, and there are some electrons within these positions. I'll mark them electron as green, and some places where they can move, free places, and these electrons can jump between different energetical positions and change their position within this metal. They can have the discrete spectra of all energies, but we will consider the case where they can jump in every position here, and we see the following situation, that electrons can be positioned in every point within this area, and it can be shown that if we will represent some x or x from 0 to 0, from minus infinity to 0, yes, we will see that we can position electron here. And in the same case we have this area. It's represented in the graph. There is some potential barrier. This potential barrier is realized by different Coulomb forces, and that attracts these electrons. And that's why every electron, from the classical point of view, can't cross this region without spending some work of exit work. But from classical point of view, there is a possibility for this electron to realize some channel, to jump in this channel, to throw from this channel, and go outside without spending any energy at all, and then he'll leave this region and close this channel, and we have electron here. And I have represented in the following form. For example, electron here, then it opens some channel, for example, yes, and it's here. But if we, from the classical point of view, if the energy of the electron is lower than this barrier generated by some electronic forces, from magnetic forces and different nuclear forces at the same period, it can not penetrate this area and come here, but from the quantum mechanical view it's possible. But you must understand that the problem is not from the approach of understanding this problem, but the main problem is the consideration of the structure. We can't consider the electron from the classical point of view at all. There are some cases where there is some ideal free electron and it flows through the space and there is some field somewhere, but in reality we don't have so cases. And that's why we have some density of the particle to be dispersed here, the particle is dispersed here, and we have some density, middle density that can be represented by around, and we have some, can this be localized, but they can cross each other. It's a quantum mechanical understanding of the area. There is no such electron as a particle in this case. There is some wave function that can be describe the position of this in this area. And here you are. Is a practical, is a quantum mechanical case, and they electrons in reality they have any interference in each other, and they different psi functions that can describe the probability distribution, and this function has the maximum position where it can be displayed there because it can be much more wider, but the most important unit of this quantum mechanical psi function has its maximum in some region. And the selection on this one-dimensional case is can be understood that we have some forces for example, in radial direction. And that's why we must understand that we don't consider the problem of quantum mechanics and classical mechanics. From the classical point of view, this problem can't be discussed at all, because in reality, when we consider the case of one electron, we shall consider, of course, some area of density distribution. And let's consider much more attentively this case. Okay? Okay. Let's write Schrödinger equation for two areas. 1, 2, 3 points. We can imagine that we can write it's in the following form, for example, minus, or let's not write it, minus h quadrat na 2m d2dx quadrat. It's a one-dimensional case, okay, so we can introduce the one wave function in the area 1, and it's equals energy spectra and this function. For example, we don't have in the area 1 any potential fields. In the second area we have the following Schrödinger equation, and you must understand that if you want to solve the problem of quantum mechanics, you shall write only you have to write only Schrödinger equation, and then is a problem of some mathematical techniques of the solution of this equation, building the realized spectra and so on. And that's why it seems I don't think that I can give you the whole solution of the task, but I'll present that it's only the problem of mathematics, the federal solution. Okay, and now I have written the Schrödinger equation for the second area. It's very simple. Second area, potential U0 and kinetical energy, but in quantum mechanical representation. It seems to me it's not so difficult. Okay. I hope I'll try to introduce you much more clear everything that will be taught here. And let's write the third equation and the third area. Okay, and here minus h quadrat 2m. And you can ask me why I write such type of equation. This is very simple. It's only the Schrödinger equation on stationary conditions. It's not a time-dependent Schrödinger equation, okay? Plus 0 at the potential. Well, max is the 0. There is no field, so it's now a model. We have model solved. For example, there is only potential here, And in our case, I can rewrite it, for example, potential electron here, some force fields acting as this region, if we have some electron here, and the other region of this where the electron is absolutely screened, and the region where there is no field too, and one-dimensional case, and well, not so, no some what. Or it can be understood that the kinetic energy is much more than some potential energy, all forces within this area. Okay, let's write the Schrödinger for the first area, and we gain all this Schrödinger. Okay, we have written 3 Schrödinger equations, and after solution them, we will gain all we need. And so let's song is the Beatles sing "All We Need Is Love," but in this case, so all we need is the coefficient I'll represent it. Okay, and let's consider much more attentively this first equation. Minus h квадрат minus 2m d2 px квадрат psi1 in the first area, and epsilon epsi1. Happiness. I see some happiness. Okay, we have written it, and let's try to solve it. Take all this unit to the right side and rewrite this equation in the following form. Psi yes is equal multiplication to masses and division Planck constants. So I'm happy I have seen this differential equation. It's enough simple. It can be solved. It's very, very simple form. Okay, and let's solve it. But let's make some changes. Let's introduce some K1 parameter, and let's write it now. Okay, I'm absolutely happy when I'm doing it because it's very simple. It seems to me that all problems that caused in with the quantum mechanical are not so difficult in reality. It's only the mathematical representation of micronature. And using this video, so I try to introduce it, and I'll try to help to the other people that think in other way or have some difficulties. And of course, understand quite much more better by myself. When you teach somebody, you understand it's better. Okay, we have written the differential equation. What is solved? How could it be solved? Very simple. Let's introduce the usual method alpha quadrat is equal minus k1 square, and the solution can be written in the following form. This is the usual technique of solution of such equation. Exponential minus equal 1 x plus c2 exponent equal k1x. It can change. It's not so important. And now, what we have seen? We have seen the solution of this equation. Okay. And next, let's use the secondary equation in this form, written in this form. C2 strich equals minus 2m h quadrat. I'll watch it back. I'll take this letter and only send it here with the backwards minus. And the main difference from the above mentioned equation that without that instead of this energy we will have only the difference of this energy and the potential U0. The potential of this barrier clear. Okay, it's written. Wonderful, perfect quantum mechanic. Okay, and let's introduce the second parameter k1 to k2, but let's see this much more attentively. I have marked here K1 that for only for that I'll have a possibility of writing this C1 function in the following form, and K2 can be written in the following form. Why? Because it should be it should contain no complex numbers. But if we have epsilon lower than 0, this is lower than 0. You understand me? And that's why we can rewrite it in the following form: minus minus And in the following form, this equation takes this view: k2 square c2. Oh, excuse me, some noise. And the solution of this equation will be absolutely the same as mentioned above, but instead of complex numbers, we have only exponents. Where I said that we don't have some C3. Oh, let's mark it as B and B streak. It's much more interesting for me. K2x plus B streak K. Oh, excuse me. K. Oh, not. Or not. Exponent minus K2x. It seems to me everything clear. We don't have any complex. The function in the third area is absolutely the same as the first one. No fields here, no fields here. Some constants. So S, C, and C3. Exponent minus or plus ek1 x plus c strich exponent minus ek1 x. Okay, we have found them. And let's watch at this final function much more attentively. And let's see what we have marked here, what we have gained here, here, here. As we'll see at this third function, we can consider this function null. We cannot. It's not so useful to consider this unit. I'll explain why. The wave function represents that we have some wave where we have plus ek1x exponent. It represents the some wave in this direction, and in the back one when we have minus in this exponent ek1x. It means that the electron flows here and it can cross this area, and after this area it will have there is no changes within this area. We don't need any energy here. It's external income. It's only external effect, and here Q1 with plus sign, and of course with negative. But the condition when the electron moves backwards is absolutely impossible, and that's why, and the possibility of this case is very low, because we can flow from this potential barrier, it has an energy less than, and it's backwards. That's why we can consider only the case we have only positive direction of this electron move. And of course, the wave function represents the probability of the electron to have such direction as such, and only the electrons that have only positive direction can pass through this barrier. That's why we can say that this only has the probability 1, and this some constants that can influence, that can have any influence only on the resulting coefficient. As a result, we want to understand only the final constant of this and the final amount of electrons that pass through this barrier. You understand me? This we must understand only the final constant of this wave function. We must understand only this constant. It will mark only the whole amount of pass through and the whole amount of particles that have used this tunnel. On another case, the stream, it can be marked as a stream. And let's try to express this coefficient C and find the final solution and the final form of this equation, coefficient. It will mark the amount of this penetrated this barrier. And I'll explain, of course, the complexity. In the case that we have not any perturbations, and we have only, for example, this some wave in the form. But here we can have some fluctuations, and we can have exponents without any complexity. But here, perhaps we will have exponent with complexity. It can be and the solution should have something like the form of like this. I'll try to draw it in the following form, which means that on this that boundary condition should follow to the connection of these functions. And let's write this in the form that C1 converts to C2 at 0 and C first derivative at the point 0 at the boundary converts to C2 derivative, because we don't have any motivations for this function to have any jumps and special changes. For example, we have some wave function, then it has some interesting form, and then we'll continue to have this function. And in this case, we can have the exponents without any complexity, but if we'll have it here, we'll gain problems on the infinity. That's why in this case, of course, it's have some physical meanings that we have gained as following form of this function. And you must understand this function marks the result extreme. Okay? And C2 A has the following form. It means that function in the area of 2 converts to the function in the area 3, and there are no difficulties at the boundary. Okay, and the resulting derivatives are the same. Okay, or not? 3 and the second one C'(A). And it's enough for the writing the some equations. And let's make it. Okay, we'll have this one, and we have gained this from the mentioned above understanding of this process. And let's write using these conditions some further equations. C1 at 0 is equal to C2. This means 1 plus C2 is equal to B plus B'. B I'll consider the first only these equations. B e exponent k2 a plus b strich exponent minus k2a is equal to c exponent e k1a, and some further relation k1 minus ak1 complex number e. Oh, it's c2 because a is equals b k2 plus b strich minus k2, and again some additional equation b k2. Oh, you'll see that we will have some interesting equations, and maybe you must understand that everything that I write here can be realized only after differentiation of some differential operations of the mentioned above equations. I mean, for example, how I have gained this the last equation then from what equation was used. For example, it was used, this equation was used, but for representing this equation was used only this equation. For realizing this equation, and everything that I was done, it was, for example, c from 0 is b plus b strich. These exponents from 0 are equals to 1, and this c1 1 plus c2. So also what is the unit? Is this equals k1 e c exponent e k1 a. Okay. It's now main task is representing this coefficient. It seems to me these operations are not so difficult, but I can give you some advice how we can represent it. First, we must use this equation and represent C as a function of B. From here, for example, we can make the following changes. B exponent k2 a. We will divide it exponent multiply it exponent ek2a. Divide is not so important. Not it's true. I will consider this equation. It's now I have tried only some mathematical rotations, and seems to me it's not so important. It's important from some cases, but the most important from this point of view is the writing of these equations. After this, after everything that was written, we can write something in addition. ak2a. It's b ak2a 2 minus b strich e k1 k2. This method can only simplify the way of finding the c. There are numerous methods, of course, of the solution of these equations. It's only the simplification. ak2a. We have multiplied here, and we will multiply it here too, and divide exponent ak2a and in division on K2. Okay. And we will present after we can sum it, so I can find the difference, and I will represent C as the function of B. The function of B, yes, it will be a linear function of B, and C f best for example. Then can be the function can be equal to each other, and after this step we will gain the following relation between B coefficient K2A 2 no, K2 plus EK1 equals 2 best 3 K2 minus EK1. And then we will use these first equations, this equation, and this one. For representing B and B' through the C2. And after this we can find the final form of B as a function of C2, and it's going to be sent here, and B' has another function from C2. Okay. And you'll write some equation, and after this step we'll find C2 as some as the result as suffer from the energy and so on, and then we will write B as function fc2, and then use this formula. This connects C and B. That's all these steps. And after some difficult permutation, we can find this. Our final coefficient C, this is the most important for us, is 4k1, k2, e, exponent ek1a. K1 plus ek2 squared exponent k2a minus k1 minus ek2 squared exponent minus k2a. And after finding the coefficient of penetration of some previous stream of falling particles divided as a stream of pass-through tunneled particles, we mark, so we will write it as Sk1 and not 0. Sk1 is a quantum mechanical issue in model C. That's a negative part. Yes. So this means the coefficient of the tunnels from faults, okay, is equals to the model of c squared. And after some work with complex numbers, they are not simple, I understand. But in this lecture, I'm not so really interested in introducing all absolute steps. So the result is will follow to the growing up the time of this lecture. But the most important feature that I want to show here some practical methods of representing this this form of this coefficient. Okay, -1. And of course, this practical implementation of this quantum mechanical and why we write so difficult and interesting formulas. Okay, and this is falling your tunnel, and there are some mirrored units. Let's watch this condition again. Barrier, falling, mirrored, tunnels. It's mirrored unit and it's falling. We have, of course, some amount of this of the falling wave, and this wave is described by the wave functions mentioned in the Schrödinger equation, written in the Schrödinger equation. And what we have gained? We have gained the amount of tunnel from the falling. And using this technique and this coefficient that is connected with the potential barrier and the energy of falling particles, its masses and constant Planck constancy, it has enough difficult form function dependence. What we have gained as a result, why we have done this all work? Let's watch it again. We have, let's imagine, we have some surface. It's nanometers and it's nanometers scale, and there are some structures on the surface. And let's imagine that we have some tunnel microscopy. Why we have measured tunnel? It's used tunnel effect. That's this is connected with PC. That independence from these coefficients is have signal, for example. And I can mention that the electron emission from the ends of such cone structure, so from is much more easier. Yes. That's why we can determine here that the resulting signal will be higher. Oh, it's, for example, the jump. And the potential, the current within this wire will be stronger in this case. When this channel microscopy falls to this well, the signal will be lower. And so on. And using these effects, we can, for example, at some x, we can build the structure of the surface using this effect of tunnel microscopy, for example. Of course, there is a dependence from the fields above the surface, but let's imagine that we have some structure. We don't introduce some fields within this unit of area. We don't influence on the electron conditions using some light and its mirroring, its one and fluorescence. We only use a quantum mechanical cold emission of these electrons. You must understand why it has a very practical, serious practical implementation. We don't influence on the conditions within these microvolts. We only use the cold emission of these electrons that can be determined by the, for example, fields above this area, but not within. And we don't need any light. For example, if you send a light, it can change the structure after mirroring, and we will not introduce the final and the previously mentioned form, and so on. And using this tunnel effect, so we will use it here then, and we will build this surface again and again, and so on. And only using this tunnel effects with this coefficient, we can apply this method for tunnel microscopy. Thanks for your attention.